So now that we have formal definitions of the stable matching problem, we can talk about algorithms for it. So what's a simple greedy algorithm we could use? We'll start with any perfect matching, any matching at all, and just check if it's stable, then we're obviously done. Otherwise, find an unstable pair, we can fix the unstable pair, and then recurse. So what do I mean by fixing an unstable pair? Well, if we know alpha prefers B over what it was assigned, and B also prefers alpha over what it was assigned, well, we can just add the edge alpha B to M, and also add the edge beta A to M. So basically, we just swap partners. That's one way we could fix an unstable pair. So this is one natural thing we could try doing. Just keep iteratively fixing unstable pairs and just hope all of them get resolved fast. But actually, this won't be the case. So let's consider one example. These are the doctors, Q, R, and S. The hospitals are A, B, and C. And these are the ranked preference lists. So these are the top. These are second place, and this is third place. So in this example, if we use the matching AQ, BR, CS, then that will be unstable because A prefers R over Q, and R prefers A over B. So AR is an unstable pair because we'd rather place A with R. So what we could do is just swap that. So we just put AR there instead because we know that makes that pair stable. And then that inherently causes us to make a BQ. So just like the example here. And we can keep doing that process. So we find another unstable pair, specifically CR, and we fix it. And we keep doing this. But the issue is if we keep undoing instability, we actually end up with the starting configuration. So we end up where we just started and we get an infinite loop. So not only won't this algorithm be correct, it just never stops. It's not even an algorithm at all. So this strategy doesn't work. So let's try a different strategy. This one actually will work. This is the well-known Gale Shapley algorithm. It's sometimes also called the Boston Pool algorithm because of how it originated, where it was actually used to match medical students in Boston. And what does this algorithm do? Well, it starts out with everyone being unmatched, and we will tentatively match some nodes. So until all nodes are matched, specifically all nodes in L, but that will also imply all the nodes are matched, we're going to look at any hospital that's unmatched, and we'll have them offer a position to the best doctor on their preference list who has not already rejected them. So what A is going to do, we could draw A's preference list, and maybe A's top choice was, say, beta, then alpha, and then gamma, and then there's others, say maybe there's pi and tau. And maybe A has already tried offering to beta and alpha, but they ended up rejecting A for something else. So what A would do in this round is it would offer to gamma, because gamma is the best option A has that has not already rejected A's offer. So A is going to attempt. It'll just offer to gamma. So that's from the hospital perspective. So that's what the hospitals are going to do in each round. Now, what the doctors are going to do is they are going to, if they're unmatched, they will tentatively accept their current best offer. So in this example, gamma would tentatively accept. So they tentatively match with A. And if alpha already has a match but prefers A, then alpha will reject the current match and tentatively start a match with A. So if that were to happen, say gamma was previously, so now rejects B, B is now free. So in the next iteration of this algorithm, B would offer to someone. Otherwise, alpha just rejects the new offer. So in particular, maybe in this case, gamma actually really liked A, then gamma would, or if gamma already liked B more, gamma would just stick with B and reject A outright. So then A, we would go to the next iteration and A would offer to pi instead. And at the end, all the doctors will accept the best offer they received. So let's look at an example of this. So the ultimate output of this is just going to be a set of pairs, a matching, but we're going to visualize this as an ongoing process of offers and rejections. In reality, the doctors only see their final offer. They won't ever actually know that we were doing this kind of process in the algorithm. They never actually see that. They just see the final offer, but this is kind of how we think of it. We can imagine that people are doing these negotiations. So in this example, we start with A. You could really start with any of them, but we'll just start with A. So A prefers little a the most, so we tentatively match A to little a. So now we go into B. B prefers A the most, so B is going to make an offer. Now A looks at its options, and A likes B way more than it likes A. So what little a is going to do is it's now going to reject A's offer. And so A has to update its list so that little a is no longer an option. And this now becomes a tentative match. Then we go the next round. We go back to A because it's unmatched, and it makes an offer to little b. And again, we tentatively accept that offer because B has no other offer. Okay, now we go to capital C. It's going to make an offer to D. D has no reason to not accept because it has no better options right now. Now we go to D. D makes an offer to A. Now A currently has its best option, so A is going to reject. A says no to D. So now A is going to try B. Again, B already prefers A over D, so B is also going to reject. Okay, now D's to little d. Little d also prefers its current match C over D, so it rejects. So at the very end, its only option is C. So D will match with C. And C has no other offers, so it has no choice but to accept. And at this point, everything's been matched. And so we stop. And that's the final matching we output. AB, BA, CD, and DC. So this is how the process will actually go. It's a series of offers and rejects. And every time we get a reject, we have to update our preference list. And over time, these preference lists go down, And similarly, A's preference list on the left side, the doctor's preference lists keep also going down. They actually go up, actually. So here, A started with an offer from A, but it got something better. So now everything below capital A was no longer an option. B got an offer from its best, or not its best, but almost its best, capital A, and so C and D were no longer an option. It would never consider C and D because it already got something better than that. Now for little c, it immediately got its best option, so it would never consider anything lower. And then little d, it was first given the option of D, but once it was eventually given C, it no longer would consider B because that would only make things worse. So you can see what happens is for the hospitals, their preferences keep going down. They keep getting worse options over time. But on the other hand, for doctors, at each iteration, their options get better and better. So for doctors, options keep improving. So from the hospital perspective, they no longer have a chance of getting their best, whereas from the doctor's perspective, they'll never get a chance of getting their worst. So it looks like things are going really well for the doctors and pretty badly for the hospitals. So that's the algorithm. So what's the analysis? So the idea here is we're going to essentially consider all n squared pairs. Because at any point in time, at least one preference list gets reduced. So either a hospital or some doctor's options are reduced. And so we remove one pair from consideration each time. And so in total, we'll do this at most n squared times. So overall, it's O of n squared total. Okay, so we know it's pretty efficient. O of n squared isn't bad, and this just comes from the fact that we basically try all possible pairs. But now the question is, well, is it even correct? Will this be a perfect matching that's unstable? So the first thing we notice is that, in fact, it is a perfect matching. So why is it a perfect matching? Well, by definition, we don't stop until everything is matched. And eventually, something will get matched because we have some kind of preference list here. And at the end, C is given an offer because there's only so many options the hospitals have for offers. So if A, B, and C already offered things to other people and got matched, then there has to be another hospital that can offer something to C. Just because the fact that D can't be assigned to B and A assigned to B at the same time, because it's a matching. You can't have shared edges. So this isn't possible. But basically, it's the pigeonhole principle, right? You have n items eventually matched to n minus 1 things. That can't happen because no two things can share one spot. So everything's going to be assigned a unique item. But I think it's pretty clear why it's a perfect matching, because we don't even stop the algorithm until we've matched one thing for every doctor and hospital. The hard part is showing that the matching is stable. So why would it even be stable? If anything, it looks like it's unstable from the hospital point of view because they end up getting really bad choices. Like here, capital D gets its absolute worst choice of doctor. So why is that stable? Well, let's consider some alpha A and beta B. We want to show that alpha beta is not an unstable pair. And so if all pairs are not unstable, the whole matching is stable. So let's assume first that alpha prefers A over B. So if alpha does prefer A over B, then we're done. It is stable. Alpha would not reject A for B because alpha likes A. It has no reason to leave A to go to B. So now let's suppose that alpha actually prefers B over A. So based on how the algorithm goes, we know alpha doesn't get a better offer than B. Than A. So we know A was alpha's best offer. Otherwise, alpha would have rejected A for something higher in its preference list. Okay, so in particular, this implies B never offered alpha a position. Because in particular, B is one of these places that have a higher preference for alpha and that didn't end up getting accepted by alpha. So it must be the case that B never even offered alpha a position. But based on the algorithm, we know B always offers to highest doctor or node in its preference list. Which means, because B and beta were matched, that implies that B prefers beta over alpha. Now, what happens last? Well, if B prefers beta over alpha, then that's not an unstable pair. B has no reason to choose alpha over beta. B prefers beta. B is happy with beta. Similar to here how alpha was happy with A. No reason to leave. So in either case, we know that the pair alpha B is actually stable. So overall, we have the Gale Shapley algorithm is correct. It computes a perfect matching, and it's a stable matching, and that's all we really needed. And it's pretty fast. It runs in O of n squared time, depending on how you're going to implement the exact operations. So now one more interesting thing about this algorithm is that it will always be best for the hospital perspective. So the algorithm always computes the best possible stable matching from the hospital's point of view, which is also the worst possible from the doctor's point of view. And this is because for any hospital A, it will always get the best or the highest ranked doctor that it could have gotten in any stable matching. So in other words, if it's possible for A to be matched with someone without it breaking stability, then this would be the highest ranked one it could get. Meanwhile, worst, well, this is the lowest ranked hospital the doctor could get in any stable matching. So this is interesting because when we walked through the algorithm before, it looked like the hospitals were getting screwed over. Their preference list keeps getting lower, meanwhile the doctor's options keep getting bigger. But actually the reality was the opposite. The hospitals end up winning in the end. They get the best doctors they could have gotten, whereas the doctors are generally matched with very low-ranked hospitals in their preference list. And so naturally, even though this is a stable matching, you could argue it's not really a fair matching. So one thing people did was just swap it. Have the doctors make offers first, and so the doctors now get their best. But there's a lot of research now on how to define some kind of fairness constraint in finding matchings according to some certain fairness conditions. And that's a really interesting and open line of work in algorithms and game theory.